Okay, so welcome everyone in our 23rd Shiksha Anusandhan Weekly Academic Lecture, which is organized by Computer Science and Engineering Department, ITER. Today we have Dr. Jubin Mitra, who is actually right now the lead electronics engineer in the physics department at the University of Oxford. Dr. Jubin Mitra has got over 9 years of professional experience. He has earned a PhD in engineering science in 2018 from the Homi Bhabha National Institute Variable Energy Cyclotron Center in Kolkata. He subsequently pursued a career in hardware cybersecurity, completing a year-long postdoctoral fellowship at IIT Kanpur. Following this, he moved into the field of radiation-hard electronics, where he spent years as a postdoctoral fellow in CEA Saclay, France. He is now working as a lead electronics engineer in the physics department at the University of Oxford, United Kingdom. So I would request Dr. Jubin Mitra to start his lecture. Jubin, are you there?
Yes, I'm there.
Okay, so you can start your presentation, and if possible, can you switch on your camera?
Give me a second. Yep. Am I visible?
Yeah, Jubin, visible.
Okay, thank you. Thank you, Professor Rohrav, for this introduction of me, and very happy New Year to all the participating members before I begin with the talk. And Professor Rohrav, should I start or wait for more members to join?
Okay, you can start, Jubin.
I can start or yeah, okay. Just hold on a second. My PPT is visible on the screen or?
Yeah,
is
yeah,
the
Jubin, visible.
visible? Okay. Yeah. So before I begin the talk, it's important for me, is the people more from the computer science or from the electronics background?
Most of the students, actually all of the students are from the computer science background.
Okay, that's okay for me. Yeah. So as the name suggests, a very brief introduction to hardware acceleration technique. It's, to be frank, it's a very, very vast domain. And within the engineering stream, as you can see, there are multiple subdomains that are originating. Like you already got electronics and instrumentation, then electronics and computer science, and electronics and engineering department. So you can see there is a branching of stream going on. And this is happening because of the upgrading of new technologies and new expansion in the technological domain. So I have built this content of this presentation into three different threads and try to knit the thread gently. And feel free to ask question or interrupt me in between the talk. I want it to be very interactive. Section 1, why we need an hardware accelerator. This is a very important part to understand, like in which type of world we are heading into, like how this technology changes are coming and interfering with the society. The second is the connection topology and the application of FPGA. FPGA is, just for the timing, think of it as an accelerator, the persons who don't know. And for the third is an application of the FPGA in high energy physics. So I'm going to briefly walk you through different domains with a very interactive session. And I hope I'm not going to overload with too much information for the student. So let's start with the first question. What is hardware accelerator and why we need it? Ray Kurzweil, an American computer scientist and a futurist, and I quote from him, And I'm reading his code verbatim from my screen. An analysis of the history of technology shows that the technological change is exponential, contrary to the common sense that is intuitive linear. So we won't going to experience 100 years of progress in the 21st century. It will be more of a like 20,000 years of progress at today's rate. The returns such as chip speed and cost effectiveness also increases exponentially. There's even exponential growth in the rate of exponential growth. But this is a very vital term we need to understand, that we are not only facing exponential growth, we are facing exponential over exponential growth. The last line actually highlights that. Indeed, we find not just simply exponential growth, but double exponential growth, meaning that the rate of exponential growth is itself growing exponentially. To justify and clarify this statement, I will walk you through some of the laws that exist in current literature. Some are new, some are very old. You all already know that. The first one is the Moore's law. He used to work in Intel, and he introduced this law by his observation that over the history of computing hardware, the number of transistors on integrated circuits would going to double approximately every 2 years. Later on, it is revised to 18 months that instead of 2 years that it is doubling. And the fact is that the Moore's law is still holding with the current technology. This is just one of the exponential law. Let's walk you through other exponential law that has seen similar kind of growth. Next is Henderson Law, which is also known as the variant of the power law in a mathematical formula for calculating experience curve and their economic impact. As both time went on and production increased, the cost per unit would decrease. You can already see that effect in the price of mobile phone. Like you are holding up pretty much a very powerful computer in your hand, but its price is pretty lower than your old desktop computer. So this is the effect of Henderson law, the production. The first one, the Moore law, is affecting your computing speed, the computing area. Henderson law is affecting your price. Third is the Creeder's law, is the assumption that the disk drive density, also known as the areal density, will double every 13 months. The implication of Creeder's law is that as areal density improves, storage will become cheaper. This again has got direct impact. Imagine the day of floppy disk, and now you're holding a pen drive, which can have a size of about 40 GB in your hand, just in your fingertip. So this is the effect of Creeder's law, which is literally doubling every 13 months. And we are still seeing the growth in this sector. Next is the Nelson law. This applies on the wired bandwidth growth. Nelson law of internet bandwidth simply states that a high-end user's connection speed grows by 50% per year. This means it is doubling every 21 months. It turns out that the law has held fairly consistently for last 3 decades now, having started with 300 baud rate phone modem back in 1982. So this law tried to mention that the wired bandwidth of a cable that is connected to your lab, like the optical fiber included, it has seen exponential growth. So previously, I don't know how many of you have used the BSNL internet, like the basic internet over the landline. From there, we have seen a growth to optical, and which is actually a very exponential one. Next one, Cooper's law. This is again applies to wireless bandwidth. The previous one, Nelson law, applies to wired bandwidth. Cooper's law applies to wireless bandwidth. The law states that the maximum number of voice conversation or equivalent data transaction that can be conducted in all of the useful radio spectrum over a given area doubles every 30 months. And I don't have to mention the application of this because you are already using its effect, like 4G, 5G, all are using this Cooper's law. It's the wireless bandwidth growth. So you can imagine, like, you are putting 2 SIM and here, then there is the Wi-Fi, Bluetooth, everything, and you are using the same spectrum. And this is actually applying to the wireless bandwidth growth. You are using the same antenna area and are projecting different communicating with different telecommunication unit. And this collectively, the boom in this wireless bandwidth is holding the Cooper's law. Last one, the name applies, it's just the opposite of it, the Pure's law, but it's actually rich. The exponential growth in network address density. So when the IPv4 was introduced in the late 90s, people thought that people would have hardly scientists and researcher will going to use the internet and will have pretty much very good number of addresses. But very soon with the introduction of computer, IoT, Internet of Things, then we have the mobile phone. Now we have got 5G connections coming in, and the metaverse area is coming up, AI and augmented reality. What is happening is that we are not only running out of IPv4, which is already we have exhausted, we are also running out of IPv6. And this was not anticipated. So there is an exponential growth there also. So why I walk you through so many types of law? Just to justify what Ray Kurzweil at the beginning of the slide I have pointed out, trying to say that we are riding on double exponential growth, that is exponential over exponential. Last one is the Kumi's law. This is still holding up. This is the energy efficiency of computer doubles every 18 months. This is like when you're asking your mobile phone to be off for a long time, minimum charging time, maximum productivity, you are actually using the Kumi's law. Just remember how the Nokia phone used to stay charged and how your smartphone with so much of capability still staying charged all throughout the day with so much of capability. This is Kumi's law. Now, together, all this law, as I put in this slide, the Moore's law, the Henderson law, the Creeder's law, the Nelson law, Cooper law, Pure's law, and lastly, the Kumi's law. All this put together, you can see all of them are exponential. Not a single of them is linear, apart from the Nelson law, where we can say a bit of linearity, but most are exponential. So you can understand that we can't keep up with normal linear thinking, normal hardware design, a normal way of approach cannot keep up with such kind of a growth. To handle such an exponential expansion in all the domain, we need a different kind of a hardware architecture, different kind of a thinking, and different kind of an entire designing approach. And this has led to the birth of accelerator technology, hardware accelerator technology. In the next slide, I just want you to show how much of data volume has grown over the years. Initially, we are operating in megabyte, that is events generated per channel. This slide I have taken from a physics slide. Ignore the first two. Let's start from the terabyte. Terabyte is actually an experimental data that is transmitted per second. And this I'm talking about 2019. Second is the petabyte. Petabyte is actually a data run by an experimental setup, a large high energy physics setup that is set up in Geneva, Switzerland. It actually generates a petabyte of data just per year. Next is the exabyte. That is the generated over an experimental lifetime. The zettabyte, that is the World Wide Web one-day broadcast information. Just imagine that we are right now, within today only we're going to generate a zettabyte of data. And the last is the digital universe of today, which is yottabyte. And it is presumed that the bronchobyte will be, we have to count in that size from 2030. That is the digital universe of tomorrow. So here I want to end the section 1, which highlights why we need an accelerator. In section 2, I'd like to introduce you to the FPGA topology, why we need an accelerator, what type of accelerators are there, and how it is connected. Any question in section 1? Okay. I'm moving to section 2 then. In section 1, we have understood that why we need an accelerator. But what I haven't talked about is what is meant by accelerator, like what options we have got. Currently, the CPU itself can be an accelerator. If you know how to program, like there is a class of programming called Ninja programming or embedded C programming. And if you can write a driver, you can do accelerated algorithm in the CPU. And for that, there is a limitation. The CPU is a very sequential way of writing a code. And hence, you can use accelerator when you know the model is small, the data set is small, and when you know that when you have to explore the data design space exploration. What is meant by design space exploration is that, say you know you have an area, the power, the algorithm, and the application. You can run the MATLAB, do some quick computation, and to guess the idea, this is the amount of computation we need, amount of model we need, amount of data we need. And for that kind of a purpose, CPU is a very good environment. Now, when you go to the next level, that is from small to medium, that is medium to large model data set, you are entering into the image or video processing area, that is the GPU, graphics processing unit. In the graphics processing unit, the processing unit are arranged in form of a matrix. The matrix are cascaded serially. And the data, when it is coming, it's actually like a water running through a filter sieve. It is flowing and it is simultaneously getting processed. So the language that is used to program GPU, it's CUDA, C-U-D-A, CUDA, it's or OpenCL. OpenCL, as the name suggests, it is open to anyone, and CUDA you need to purchase a license. So graphic processing unit, you already got one in your CPU. Either you are using AMD or Intel or NVIDIA. And the games that you are playing is actually running on GPU. Just for example, an algorithm that is run in GPU, when you are playing a game, there is a shadow of the character that is falling on the ground, or maybe the reflection that is falling on the water. So what you are actually doing is that you are computing a cost component of the model and you are projecting on the ripples of the water. When you are doing, it seems very easy, like a cost component of a model, how tough it is. But when you are, the character is running and you are projecting the shadow on the ripples of the water, it's a very computationally complex job. For that, the GPU does that thing for you. And when you are running the game, you don't even realize that such a complex computation has gone behind it. So that's the application of GPU. Next is the tensor processing unit. This, as the name suggests, is for matrix computations, dense vector processing, and no custom TensorFlow operation. So tensor processing, as the name suggests, it is much more efficient for different type of correlation, covariance, and matrix computation. So when you are doing fluid dynamics, this from TPU it comes to a bit of research domain. When you are going to do fluid dynamics, you need to calculate the correlation, covariance, standard deviation, and matrix and eigenvalue, all those linear algebra components simultaneously. You cannot wait for a microsecond delay between this. For such kind of a computation where you know all the different matrix computation that you have to do, in that case, TPU is your choice. That is the tensor processing unit. The fourth one, which I will going to explain today, is the FPGA. FPGA, the beauty of the FPGA is that it can act as all the upper three components, that is the CPU, GPU, and tensor processing unit. You can actually write your own algorithm, parallelize it, pipeline it, multiply it, or even scale it. You have the choice. It is applicable for computer intensive application where you know the large data set. It's a very high performance application. I have mentioned all the pros about the FPGA, and the cons about the FPGA is that the programming of FPGA is very challenging. When you have got CPU, you have C, C++ where you get the error handler to tell you, you have missed this semicolon there, you have done such a mistake there, maybe there is a memory overflow there. But when you are going into FPGA, you really have to be very strong in your domain to understand what type of error is there, because the compiler, synthesizer, fitter, no one going to help you that your algorithm is wrong. You have to understand yourself, and by the time you realize it's wrong, you have already implemented it. So you have to be mathematically strong and understand what you are doing. But the power of FPGA is that, as I've mentioned, it can compensate for CPU, GPU, and TPU. It can perform all the three operations. On the left side of the slide, what I mentioned is, try to mention is the silicon alternatives, the CPU, GPU, FPGA, and ASIC. If you go and look at the lower section of the diagram, you can see a bidirectional arrow. On the left side, it is pointing towards flexibility. On the right side, it is pointing towards efficiency. As I mentioned here, if you write a code in CPU, so out of all these four, writing code is easiest in CPU. But when you need the efficiency, as the arrow points out, next choice is the GPU, third choice is the FPGA, fourth is the ASIC. ASIC is the application-specific IC, the full form of it. And when you are in ASIC, you have to remember it is one-time programmable. You can program it only one, or you can manufacture it once. So it's a very costly affair. But FPGA is kind of a trade-off between these two. You can reprogram it multiple times, but again, writing code is difficult in FPGA. So let's move into the next slide. In the previous slide, I mentioned about the different classes of accelerator. In this slide, I'll try to mention what is meant by heterogeneous computing. This is a very basic slide of what can be an heterogeneous computing. Currently, when you are in the CPU, you are actually in homogeneous computing. A single silicon which actually houses the CPU, maybe a GPU, and all these are housed in a single silicon chip. But there is a different kind of architecture that is known as heterogeneous system, and which are currently in large use application. As the silicon wafer, that is the base, would be the same. On it, there will be an FPGA, there can be a GPU, there can be a CPU, and even a neuromorphic hardware. In this slide, what I've mentioned is that on the left one is the multi-core processor. A multi-core means you can have the Intel i7, i10, the recent version, i9. On the GPU scale, you could have the NVIDIA GPU. This is the automata processing, like the TPU, you can have it there. Then we have the FPGA, and then a neuromorphic neuromorphic hardware. This is a new class of hardware that is coming up, and it is gaining popularity. Neuromorphic hardware is like that. It can heal itself, or it has got an analytic property. Means like a hardware can repair itself. It's a kind of a hardware which is very useful in radiation zone, or where there is a high tier and error things, or it can adapt to the environment. That's called neuromorphic hardware. So this slide highlights 5 types of accelerator that are in use in the market today. And I'm going to stick to the FPGA part. Yep. Before I move into the content that are inside the FPGA, I want to mention the full form of the FPGA. FPGA, the full form of the FPGA is Field Programmable Gate Array. The word field here doesn't mean magnetic field. It means the field in the area where the programmer is working. So the first two part, field programmable, means you can program real time within the environment. Gate array means it's a huge array of logic table. That's what it is. It is basically a large size lookup table. That's it. That's what FPGA is. What I am showing on the slide right now is a radiation tolerant FPGA from Xilinx UltraScale. So as I mentioned in the section 1, that we are in the era of accelerated technology. So we are not quite happy with the only FPGA. That is the center part, 20 nanometer programmable logic. We need something extra. We need a bit of microprocessor, like in the heterogeneous system. This left side, can any of you confirm whether the mouse is visible in my slide?
No, your mouse is not visible.
Okay, then I go by the
No,
legend.
yeah, it's visible. It's right now in TMR microblaze.
Yeah, it's visible. Thank you. So on the left side, the TMR microblaze, it means triple modular redundancy. It's a radiation tolerant. We use in radiation tolerant triple modular redundancy just for more resilient logic build-up. The microblaze is actually a very low cost, low resource hungry CPU. It's from the Xilinx proprietary CPU. You can think of it. On the right side is the DSP slice, digital signal processing slide, where you can process the digital signal. Remember, the TPU is dedicated for K-matrix processing. The DSP slice of FPGA actually provide you that kind of a capability. Then there is a block RAM where you can store a large array of signal data or a processed data or a pre-processed data in a block RAM. This is not something stored in the programmable logic. I'm coming into the programmable logic part at the last. Then there is a DDR3, DDR4, which is same as the computer. Then these are high range IOs, which can be USB, PCI Express. This last three, PCI Gen 3, 10G Ethernet. Then we can be 1G Ethernet. It can be an arbitrary protocol. It's up to the developer. So all this high-speed transceiver is directly can be connected to the FPGA without going through the CPU. That's a very big advantage, because whenever you go, a signal goes through the CPU, it is throttled by the CPU processing. And on the left side is the system monitor. Since you have such a huge system, you need to monitor in-house, not something externally. So this system monitor is situated in the same silicon. And on the middle portion is the programmable logic of the FPGA. So what this logic can do, it can actually, the connections can be routed and glide in such a way you have got a very high level of agility and malleability in logic building. So this is the very rough sketch of FPGA ultra scale top level view. Let's zoom into this programmable logic part. That is the middle section, 20 nanometer. And by the way, this 20 nanometer is the silicon transistor size that is speaking about. So currently at this is 20 nanometer because it is radiation tolerant. If you are going from non-radiation tolerant, it can be as low as 6 nanometer. That is the FinFET technology. Okay, if we zoom into this programmable logic, we are going into two different kind of a configurable block. On the left side is from the Xilinx. On the right is the Intel. Before I go into the blocks, I need to give you a brief background of the components that exist in the FPGA domain. Like in the CPU, you know the AMD and Intel. Similar in the FPGA, there are three big vendors. One is the Xilinx, second is the Intel, and third is the Microsemi. Xilinx has a much more bigger market capture in India. Intel is in the European side, and Microsemi is for radiation tolerant FPGA building. So on the left side, as I mentioned, the programmable logic is basically a large part of a lookup table. You can see it is mentioned here that 4 signals are coming in. There is a lookup table. It is going through a flip-flop where you can actually latch the value or process it, delay the value, and then it is going into a mux and a output. This is the block of a Xilinx. On the right side, you have got the Intel FPGA fabric, which is same like the Intel. It's just two blocks are concatenated. That's why it is looking like it is taking 8 units. It is again an adaptive lookup table. There is a full adder inside. That's also built on same silicon. Then we have got a mux, then a register, and the signal goes out. So this is just a very basic difference between programmable logic unit in Xilinx and Intel FPGA. till now we have understand the content within the FPGA, very brief overview on that. Next is what is the application of FPGA? Like I have mentioned to you the application of CPU, GPU, TPU. Where is the application of FPGA? Right now it is used mostly in consumer electronics. Then there is a cybersecurity area, that is this one. Then video and image processing. This FPGA is right now being used by NASA in satellite for processing of the map information. So that's what the FPGA is using. Then we have got the aerospace and defense. In the aerospace and defense sector, like you have got that aeroplane architecture. Then there is that for defense, like security blocking of the radiation tolerant and error resilient architecture. You need the FPGA. Then we have got the wireless communication, like the 5G communication is being tested right now in FPGA, 5G and 6G. For the 6G, the standards are not yet fixed, and for 5G, standards are fixed, but there are still R&D going on the spectrum area. Then we have in the medical application. For scientific instrument, I'm going to highlight one case study here. And there is other, that is the FinFET area, financial area, the stock market area, where in stock, there is a delay of a millisecond, there is a valuation loss of in terms of thousands or millions. So you really can't delay the processing. For such kind of an application, FPGA are needed. So the sector is called FinFET sector. Yeah. So in this slide, I have talked about the application. Next, I'm going into the different modes of connection. Like for GPU, you know how it is connected into the CPU. Just plug it in. The CPU does the operation and it gets back the result. For FPGA, it's kind of the same, but there is a bit of difference. Popularly in scientific literature, there are 4 ways of connecting FPGA. Inline acceleration, that is point A. Loop aside acceleration, the point B. Fast path connection, and 4th is optimized software path. For the example here, I have used 10G link. It can be on PCI Express link, can be any other arbitrary link. Just for understanding, I have used the 10G communication link here. So for the first one, that is the inline acceleration, FPGA is connected to the host processor via the 10G link. In this inline acceleration, what it does, it takes the data from the CPU, process it. It can be, for example, basic cryptographic operation also. It does the operation within the FPGA and sends it back to the processor after the processed information. Let me give you a case study, then you can get it. For example, you have downloaded a file from the internet in the CPU. You need to know the SHA-256 digest of that file. You just send that file on the FPGA, do the rest of the operation on the file, and get the SHA digest from the FPGA and tag it with the file. So what we have done here, you have saved the computational resources of the CPU. So this is the application of inline acceleration. Second is loop aside acceleration. In the loop aside acceleration, the host processor acts like a manager. It doesn't have to know what you have done. If there is an error, it will flag it. And once it gets the processed data, it will get back to the host processor. So the data can come to this FPGA from the host processor side or from the network processor side. And it gets the processed data from the FPGA in either of the side. The CPU has the option whether to get the network processor processed data or not, and it can get its own data also. So it's a bidirectional application. The third is the fast path. In the third one, the CPU really doesn't bother about what FPGA does. It asks the FPGA, handle the network processor. If there is any error, just let me know. Otherwise, keep the offload away from the processor. That's the fast path. This is actually, as the name suggests, its highest application high speed is achievable in fast part only. That is the subsection C. And this type of application is used in railway ticket booking, where the processor doesn't care what the FPGA does, it just wants the information. The fourth is optimized software path. In this case, if the processor finds that a subroutine of the software is quite heavy, let me offload it to the FPGA. Then the FPGA does the processing and gets back with the result of that part of the subroutine. And that is called optimized software path. But for the last section, I have to mention that the FPGA is not built for this kind of application, but still some people like to use it for this application. FPGA primarily used in inline acceleration, look-aside acceleration, or fast path. The fourth one is very rarely used. Okay, we have reached the end of section 2. Any question till now? Okay. Yeah.
Sir, good evening, sir. Sir, I wanted to know like which technique could be used for edge computing. Like, I think it could be different. Like for 5G, perhaps.
So
Sir,
what you're asking is you want to which in this acceleration mode you're asking?
yes, sir. Like
for edge computing, you're going to use the look-aside acceleration, B. This one. For edge computing, since you asked this question, that's a very good question. There are two sections that have come up: cloud computing and edge computing. On the edge side is actually the B, and on the cloud side, it's actually the C.
so.
Yeah. And another thing about the edge computing is that the FPGA that you're going to use need to be very power efficient. That's why it needs to be very small. And the second is that there is something called lightweight algorithm. In security, people who are in security already knows there are lightweight version of SHA-256, SHA algorithms, CSE algorithms. People used to implement that in FPGA. And that's the application in IoTs.
So.
Okay. Okay, then I'm moving into the next section. Before I begin the section 3, I am giving a case study application in high energy physics. So previously, as Rohrav mentioned, I used to work in high energy physics and CERN, Geneva, Switzerland. In CERN, I was also working as an FPGA engineer, and there I have found a very high application of FPGA in data processing. So by data processing, I mean I have to crunch data at the rate of terabytes per second. That's the speed. And in CERN, it's a high energy physics area. There are 4 separate experiments: LHCb, CMS, Atlas, and ALICE. I have worked on ALICE experiment. In the ALICE experiment, there is a block called Common Readout Unit, which actually takes data from different high energy physics detector, crunch the data, compress, process whatever it does, and pass the data to the next computing unit at the rate of terabytes per second. So next is a video of the CERN experiment. I will not going to interrupt within the video. What I want you to look in the video is the data communication flow. So initially in the video, you can see there is a big bang of 2 particles colliding each other. Multiple particles are generated. And these particles are detected by different physics detector. Then the physics detector pass those data to the electronics, front-end electronics. The front-end electronics pass the data to the FPGA. That is, in our case, it was Common Readout Unit. And from there, it goes to the computer storage, that is the cloud computing. And from there, it goes from CERN Geneva to Budapest, then to India. We have got in VCC Kolkata, one such data house. And then the physicist, after it is in offline, process the data. That's the entire procedure. So I'm going to try to show the video, and I hope it plays. You can see such thing. And look at how the data is flowing.
I think Dr. Jubin Mitra, I think the video is not sync with the Google Meet capturing speed. So I
It's
think,
dropping.
yeah.
Like, what solution do you suggest? Like, should I pause in there?
I think better. I mean, if you pause the frame and if you want to state something over there, it would be better, I think.
Okay. In this part, detected data is coming towards the front-end electronics. That's the trigger level 1, the ultra-fast selection. Then here, after processing from the FPGA, it goes into the cloud computing area. Sorry, it just keeps me skipping. Here, the data is going from the online computing system to different other computing sector. The data that is generated in Geneva, it's around petabytes of data. It's getting backed up in Budapest. From there, it is spread to different part of the world. India is one of them. The plot that you are seeing is actually the Higgs boson discovery plot, for which the LHC awarded Nobel Prize to Higgs. And as you can see, the peak is very little, but the amount of data crunched for that is around petabytes of data. So what I am trying to give you the feeling is the complexity of the current big experiments and how the FPGA helps in real-time processing of the data. Yep. Is the video observable, like what Professor Rohrav mentioned, that some parts are not getting clear, visible? Is some of the video visible? Can any of you just confirm that?
So we saw some of the, whatever you paused, I think we just saw that, the graph.
Okay.
And yes, sir.
Okay, then I'll not have to repeat that part. So previously, the architecture of the high energy physics, it's a bit of digress from the topic, but since I'm telling you a case study of high energy physics, just bear with me for some technical jargon. In high energy physics, Previously, it was a triggered architecture. Now it went to triggerless. And why it went to triggerless is that, for example, the discovery of Higgs boson particle, it can happen after millions of collision has gone through and one particle is Higgs boson. So that's the level of accuracy. What happens is in such a case, you cannot afford to lose a single collision. You need to record all the data. When you are in a triggered type of a communication system, what happens is it's actually a window. It opens the window, capture window, takes the data and drops the rest of the data. So what's the physicist around the world and engineer try to understand is that, why don't you capture all the data and then process it offline and drop the data, or real time, and drop the data on the communication channel and at the offline analysis. What happens in that case? You can capture a very low frequency particles like Higgs boson in this case. And that's why there is a shift in the architecture. And when you have such a very big shift, previously it was the old electronics, we have got the ASIC and everything. Now what happened, we have switched into FPGA. The FPGA sits at the center, that is the data aggregator part. And what the FPGA does here, as I mentioned, it crunches millions of detector data and pushes the data on the offline side at terabytes per second. And not only that, the algorithm of the physics is adaptable with time. Like every 2 to 3 months, the physicist might say, this type of algorithm, we need a bit of modification there. You can't change the electronics every time. So the FPGA is the hardware there. And by the accelerator, by now we have understand what the FPGA does. It does the acceleration. So it takes the data from all the detectors, do the processing, do the trigger operation, drop the data, process the data, compress the data, and pass it on to the DAC processor without even a single clock cycle delay, because it is happening all real time. So this type of data aggregator architecture, it's not a single thing that's happening right now. Most of the high energy physics experiment are opting for such an architecture. Just to name few for this presentation, the one that I've shown you is the ALICE at CERN, which is using common readout unit and will be applicable from 2022, like this year, but because of Corona, it will be delayed. Second is ATLAS at CERN, Felix board, which is actually the same FPGA based. Then CBM, which looks at the high density matter. That is the data processing board in Kintex FPGA. For ATLAS at CERN is actually looking at antimatter. It's quite interesting physics phenomenon. It is looking at FPGA based PCI card. Then we have got the LHCb, which they have named as Sol 40, Odin 40, Trigger 40, TL 40, but they are actually all using the FPGA at the back end, and which are different kind of accelerator. Fifth one is the ITER, where there is a fusion reaction, controlled fusion reaction. Literally, people are trying to discover how to achieve that, and that's a very big achievement if it is possible by the scientist. So they're using something called Kodak, which is actually an FPGA situated on a distributed network. So what I try to put forward in this slide in a very, I would say in a very scattered way, is that all people are using the FPGA technology at the back end, putting different name on the top of it, and building their own customized accelerated solution. That's what they are doing. So all this thing comes under the head of called data aggregation unit. This is for the understanding the concept of data aggregation unit, just a very brief overview I'm giving. On the left side is the radiation tolerant radiation zone, and the electronics on the left side are radiation tolerant electronics. The detector, as I was mentioned here, the collision is happening on the left side. Detectors are reading the data. There is a front-end electronics. In this case, it is called GBT ASIC, a product built by CERN electronics group. Then it is passed over something called GBT link. Remember, in the FPGA layout, I have told you that you can build your own customized interface link. Like for example, TNG, PCI Express, these are all commercial. If you want to build your customized solution, you can actually build that without asking for any license fees. Of course, you need to do a bit of programming there. So that's the advantage. So what we have built here is a customized GBT link, interface link, and we connect this with the front-end electronics, and all this together push the data into the data aggregation unit, where there is a bit of data traffic manager processing block. And this part of the data is bifurcated into two parts. One is the streaming data. The streaming data in this case, think of it as a video stream. That's a major bulk of the data. It is being pushed into the 10 Gbps to the next computing sector. And on the PCI Express, we have the basic control system, like the mode C of the operation that I mentioned in the other slide, the mode of communication. So this is actually operating in that mode. So this is called data aggregator, and currently most of the high energy physics experiments around the world are using this model. And as I mentioned, they're using different terms on top of it. This is just to show you how data aggregator unit, which is termed at common readout unit in case of Alice, is actually using the same architecture what I've just mentioned in the previous slide. So data is coming from in the front-end electronics, going through the GBT. There is a CRU there. Then there is a fast level processor going into the network, in this case 10 Gbps, and then it is going into the DCS, data control system. What I want you to look is the similarity between this slide and the generic slide. It's actually the same. I'm pausing here just for you to look. The front-end electronics, data aggregator, control, and this is the Alice experiment CRU, how both of them look same. Okay, so I'm reaching the end of the presentation nearly. So in today's presentation, I tried to highlight some of the pros of the FPGA, the reconfigurability. You can reconfigurable on the fly, on the go, or you can actually build the firmware. You have the advantage of huge parallelism. Like, it's up to you how better the developer you are, you can actually build your own parallelism. Then there is a pipelining. The word pipelining in case of CS student, I can tell you in a different way. Think of a water pipe. When you are continuously having the water coming out of the pipe without any gap, it's called a pipelining. If this thing, for example, the pipe is clogged, or somebody makes a closure in the pipe, the flow gets throttled. So better the pipelining, the more the throughput would be, the area of the pipe, more the pressure on the water, better would be the pipeline speed. Similarly, in the electronics, pipelining means that more the data size, the data size vector, and more the clock speed, you got a better version of the pipelining. And when you have a pipelining, you are not waiting for the processor to finish. For example, when two processes, process 1 and process 2 is happening, process 1 cannot release the data until process 2 says that process 1, you can send the next packet. Otherwise there will be a drop of the packet. So to avoid back pressure, the concept of pipelining is there. And FPGA is beautiful in doing the pipelining. You can just do any level of pipelining. It depends upon your programming style. Fourth is the rapid prototyping. Fifth is the dynamic configuration. I've already shown you. And last one, reduced time to market. I've already discussed that in the case study. So I think it's time to close the presentation. Thank you. Any question? I'm open for it.
So I have a question.
Yeah.
So for like when we are having cloud environment, so there are some mechanisms like automated scaling listener, which they predict based on the coming demand, traffic demand, the scalability is met. But so is there some is there some mechanism which can think about how we can accelerate how resources are like we so far I've not read about how hard like acceleration in terms, because ultimately it is working on a hypervisor mechanism, or it's working on a physical server through virtualization. So this can also be accelerated.
You are talking about the cloud computing, right?
So,
Yes.
so
Huh?
like it's my understanding that most of the applications would be related to matrix multiplication or a lot of parallel computing or things which need to be done in a parallel fashion, like phase detection is where hardware accelerator algorithms or like, so how does it can how it is applied to cloud, sir?
Uh, in cloud computing, first of all, you need to develop the FPGA coding in the FPGA coding nowadays. MATLAB actually supports a level of automation that makes the life easier. And secondly, for cloud computing, you need to operate in the C mode, that is the fast path mode. And so there are different sub applications. Like, you can tell me a case study, like do you want to accelerate the cryptography part or the phase detection part? Any specific problem you have got, or just a generic?
So I'm just talking in generic, like if there is some application which is on a software which is available on cloud. So if the currently the way it is executed or the time it takes, can it be further enhanced with some hardware acceleration techniques if it can be
Yes, yes. So what
implemented?
happens in the cloud is that you have got multiple core of the processor that are allocated every time you run a software. For
So,
example, if you try a GPT-3 or something, it is actually running on the server side cloud. What actually, it's not on your part. You cannot do anything on your part. It is the work of the cloud person to
okay.
dedicate different FPGAs instead of processor for such operation. So when in the FPGA, if you program that software in the language of firmware, and instead of processor core or hypervisor, as I mentioned, if you use the FPGA block, it will be much, much faster, and you can get exactly this amount of time you have to wait on the machine. So in current case, there is a very vague information that you may have to wait 5 minutes, 10 minutes, but actually you're waiting for 15 minutes.
So,
Yeah. So when you have the FPGA, you will not going to have such a non-deterministic time. It will be much more deterministic, and the traffic queue will be very low.
so, so, thank you, sir.
Okay.
Yeah, I have a question, sir.
Yeah.
Yeah. In few recent years, there has been a lot of improvement in software technology and algorithms. We are also approaching towards complex AI algorithm and data science. So, what I can summarize, the
Yep.
changes in software are very fast, and we need very fast
Yes.
computation. So, is the research and acceleration in hardware technology and improvement, is it competing parallelly with improvement of software, or is it slow?
You are telling whether the software is keeping up with the electronics growth. That's the question. Or?
Yeah, is the development of hardware is keeping up with recent
With
changes in software technology?
Yes, it is keeping up, I would say, because some of the discoveries, as I mentioned, neuromorphic hardware was developed in software. Now we have the hardware. Then you have got the quantum computing. It was previously in theory.
Yes.
Now we have the hardware. So hardware
Correct.
is keeping up. But one thing is very important to understand: like the software, the growth is linear. You are actually limited by the environment that you are in. But in case of hardware, when hardware picks up, it's actually an accelerator.
Right.
It's an exponential. So just
Okay.
go through the history. We'll see all the growth of the software is linear. It's not even linear, even lower than that. The hardware takes in, it's an exponential.
Okay. Thank you. I think no more questions.
Okay, I just have a general query, Dr. Jubin.
Yep.
So we have lots of students who are actually doing research, and we have one course in SDP for the BTech students especially, and there are so many BTech students on third year. So if they interested in the hardware domain, what type of research problem they should target in the BTech level, and for the MSc and the MTech student, they also have one project for the master degree, and the PhD students are also working here. So what type of research domain we can explore as a PhD topic, and what type of research topic we can target for the MTech and BTech student? in this hardware domain?
Yeah, yeah. So we have got plenty of domains. That's not the thing. What important to understand what type of manpower you have got. Do you got some good programmer who can program in FPGA, or it's a you got a very good theoretical person? Like whether you are good in experimental or theoretical, that's the main thing.
But what are the current problems that you can target? I mean, as a BTech student or as maybe as a PhD student?
I'll tell you to target the theoretical problem better, because that otherwise you don't have the electronics engineer. Assuming this in my mind, some of the problems is like cybersecurity. Number one, I would say, because there are multiple open areas in cybersecurity currently. For example, when you are talking about the IoT, I mentioned about lightweight algorithm and FPGA. But you are actually broadcasting the data on the wirelessly without a bit of encryption. So you need to develop an encryption very lightweight and low power consuming, yet it is non-breakable. So you can understand there are open areas in that area. Then we have got a very good area that's coming up in the area of fintech, that is financial area. In the stock market, number of algorithms that they need to port from old software area to the new accelerator area. There is a R&D is lacking. The third one is the quantum computing. Multiple areas of the problems are still not solved. Then the fourth one is, I would say, people are actually trying to go into different niche areas which are already existing, but when I did my PhD, I found that some of the basic problems are not solved. For example, how to compute and phase within the FPGA. I didn't find a research paper on that. Such basic solutions are not there. For example, you might find a sorting algorithm, which is a very basic problem in computer science, but it is not yet migrated to accelerator domain. For example, merge sort. You can actually propose a paper on that, like a research paper, like how to efficiently transfer the merge sort from traditional single CPU based system to multi-core heterogeneous computing system, which I have just shown you right now, heterogeneous system. So that type of areas are still open. Yeah, over to you.
Thank you, Jubin, for your nice talk. If I try to oversimplify your lecture, so Jubin is basically talking about hardware accelerator. Generally, I mean, as a computer science background, we generally first target the software. Okay.
Yeah.
So, but we need to think that whatever language, whatever algorithm we are designing in maybe using Python, Java, so we are actually using a general purpose processor. Okay, but there are so many problems when you are using general purpose processor with a high processing algorithm. So when you are targeting a high processing algorithm, it will be better if you target a hardware. I mean, FPGA is one of the, very popular solution right now. So this is the actual thing Jubin is trying to say. And right now there are lots of applications like high energy physics, especially even the post-quantum cryptography. So these are the very high processing algorithm, even the neural network, the machine learning algorithms, people are targeting this FPGA. So generally when we are going to report some research, so we need some, evidence which can be derived from mathematics and which can be derived from some result. And how we can get the result, and maybe we can implement it in simulator, and maybe we can use a hardware also. But in case, I mean, right now, if you see, I mean, few simulator results are good, but even in few simulator, they have considered all the real life constraint. But when you are going for a research paper, I mean, it would be better if you have a practical implementation. So for those cases, even for the PhD students, master student, so if, I mean, whatever algorithm you are targeting, whatever application you are targeting, if you just make a simple hardware with this FPGA, so I think you'll get more credit for it, for your research paper. Thank you again, Jubin. I would request, okay, one more thing, that we have one lab here, I mean, in C107, where we have a Vivado access, we have few FPGA also. I mean, if any BTech student, any master student or PhD student are interested in hardware project, they can come in the C107 lab. And that's all actually. I would request Bharatjyoti sir to deliver a vote of thanks for this session.
Okay, thank you, Rurup sir. I, on behalf of the Computer Science and Engineering Department of Shiksha Anusandhan University and the entire organizing team and the participants, and also on my behalf, I extend a very hearty vote of thanks to Honorable Speaker Dr. Jubin Mitra for gracing his important work and sharing with us his important findings and opinions. So this topic was very simple, very clear. It was extremely well delivered and presented. So we all are inspired by the great words. Once again, a big thank you to Dr. Jubin Mitra for your effort towards this webinar. A brief introduction to hardware accelerators from your side.
Thank you, Dr. Bharat.
And we also would like to acknowledge, yeah, thanks. Yeah, we also would like to acknowledge our gratitude to Dr. Roropal for inviting Dr. Mitra and also posing some important question on behalf of the students and sharing his willingness to improve the research work. And with this, I would also like to thank our organizer and convener, Professor Dr. Debahoti Mishra, Dr. Sarada Prasannapati, Dr. Divya Sundar Das, and Mrs. Madhuri Rao for organizing this platform. Last but not the least, I thanks all the participants for their presentation and time. I wish everyone a happy weekend and healthy time. Thank you very much, sir, once again.
Thank you.
Thank you. It was a very lovely audience, I can see. Quite interactive.
Thank you, sir.
Thank you.